Hello and welcome to this session where we are looking at the analogies among the different types of balances. So we've been focusing on this balance where we are interested in the rate of change of the moles across our space, and that's as a result of convection as well as diffusion, and possibly there's forcing. But of course, we are neglecting forcing most of the time. We don't really consider problems of forcing as yet, which you'll see much later in the curriculum. So looking at convection and diffusion and reminding ourselves that in convection, this is due to the bulk movement of a fluid, which is simply carrying our moles around the space. And then, of course, diffusion, it relates to the tendency of the molecules to spread out among the rest of the fluid. So bulk motion of the fluid and then motion of the molecules superimposed on the bulk fluid. So those basic concepts we will see again and again in the energy balance, in the momentum balance, and there's also a case in electrostatics, which belongs a bit more to the electrical and electronic engineers, but we see it has a similar form. But anyway, let's look at the chemical engineering ones. So when you do the energy balance, and that will be one of the next sections in the course, we'll see the accumulation term looks like this. So the rate of change of energy, we can see something familiar here, the heat capacity and something related to the mass, right? Of course, this is the density. So we can say this is effectively MCP delta T. So the rate of accumulation of energy is accounted for in this way. And then we can see the bulk motion of that energy. So just by virtue of the fact that the fluid is moving, we have U, Cp, and delta T. So again, when you do this balance, you'll see this term. It has the same meaning as our convective flow. So you do have bulk motion of energy as well. The change in energy simply because our fluid is in motion. So we have the bulk movement of energy. So energy is being carried into and out of the space. And then we'll also see a kind of diffusion-like term. So conduction, right? If we think of heat conducting, so if you switch on a stove and you hold your hand near a plate which is growing warmer, then of course the temperature is rising in that plate. So heat is conducting in that plate. And in fact, for you to feel it, it's conducting across your nerves as well. So the conduction of heat happens by temperature difference, right? Thermal conduction. So there's a temperature difference. So in one spot, there's a high temperature and then there's a low temperature next to it. And so heat flows from high to low, just like the molecules flowed from high to low. They diffused from high to low. So it's the exact same idea in the energy sense. And of course, you can have a forcing term as well. So for instance, if you had a flame applied to a plate, then that would in effect be a contribution to the heat or the energy of that plate. And so that would be like a forcing term. So we can see direct analogies among our mole balance and our energy balance. And by the same token, when we do the momentum balance, right? So the energy balance, we can see that's in terms of a lot of focus on the temperature here, but not just, there's also chemical potential, and you'll see all these concepts in thermodynamics. But looking further down here in the momentum balance, now the focus is on the velocity. So the fluid flowing around the system is carrying momentum across the space. So we can think of the rate of change of available momentum in our fluid. And that rate of change will relate to how much we are flowing across the space. So simply by virtue of the fact that the fluid flows into and out of the space, that is momentum that's being contributed and removed from the space. And then also, if we think about the molecules, think about differences in velocity. So think about in a fluid, in a pipeline. So next to the wall of the pipeline, we can imagine that there's some drag by the wall on the fluid. And so the fluid near the wall is a little slower than the fluid in the center of the pipeline. So there is a drag between these these different fluids, or it's the same fluid, but the fluid at different positions. So the fluid near the center is flowing faster. It's tending to drag on the fluid near the wall. And this is accounted for with the concept of viscosity. And in fact, this is not purely abstract to us. We can easily imagine, for instance, the flow of honey. So imagine, let's say not a jar of honey. Let's say we have some kind of channel, or what's a cooking type of thing? Okay, just imagine a glass of honey, right? Now, if you imagine trying to swirl it with your finger, you will experience a certain drag on your finger. And that's because when you drag your finger through that honey, the honey that's at positions a little further away from your finger, they have a velocity of 0, whereas you are forcing your finger to move with a certain higher velocity. So the drag of of one part of the fluid on the other part of the fluid, that we account for through this concept of viscosity. And there you see that drag, that force is diffused. It's a form of diffusion as well. The viscosity, the difference in velocity is the driving force there. So just imagine a fluid which is trying to flow, and the base is moving faster than the rest. Then the base will drag the fluid at the top. And that's because of this viscosity, viscous drag. So we can think of it as electrostatic attractions between molecules at different positions. So that fluid will drag itself according to the differences in velocity. So just like in diffusion, we had differences in concentration. Like in the energy sense, we have differences in temperature. In the momentum balance, we have differences in velocity, and that drives a certain force. So when we try to move our finger through that honey, we experience a certain friction force. And so that force we account for through this concept of viscosity. So we can see the same 3 terms or 4 terms. I mean, we can always apply forcing to this as well. So for instance, if we try and pump that honey around, then that's simply energy that we are forcing into the system. So there's that. So the same 4 terms arise in each case. We've got accumulation, we've got viscous flow. So just because things are moving around, then it's carrying into and out of the space, whatever it is we are trying to balance. And then we also have the tendency of the molecules to diffuse away from that bulk motion. So as much as we have clearly defined 3 different concepts, or like we said, there might even be 4 different concepts when we look into electrical engineering, it seems to us that there might be something more fundamental even than what we operate on. So it appears that perhaps there's a certain transposition that's needed, that instead of thinking in momentum, heat, and mass transfer, we should be thinking about convection and conduction like things. So those, it appears there are these 2 fundamental or 3 fundamental types of things that happen when we consider a fluid and its tendency to move and things like that. But anyway, in engineering, this is how we view a fluid in terms of those 3 main things, and possibly 4 things. And so we can see that there would be analogies among these 3, that because the same types of things are driving each other, there should be some way to relate what happens in the one to what happens in the other. And so if we think about this, there are a couple of important parameters that we can start to see here. So for instance, the heat capacity, that's an important parameter that tells us how much the energy will, or how much will the temperature rise if we put a certain amount of energy into something. Then the conduction, that tells us how fast does the energy tend to spread out. Similarly, diffusivity, how fast do molecules tend to spread out across our fluid? Here we have the momentum, so that's a well understood thing in terms of the convection. in terms of the conduction-like operations, viscosity, that is the important parameter there. So we can see that if we want to solve equations of this type, then we likely need all these parameters. And so that is something of a concern to us, that we do need a number of parameters, these constants. We do need them to solve the equations. We know also these equations are not well, they are well defined, but there is a significant amount of work to solve these equations, especially with complicated geometries. But anyway, we at least have these relationships. So we accept these, that there are some analogies at play here. And then we start to think about what happens when we start looking at solutions to these. Well, before that, what we can also think of is identifying so-called dimensionless groups. So if we think of the parameters like we just mentioned, we have the viscosity, we have the density, we have diffusivity. And if you check the units of these parameters, right, you would find that there exist certain ways to group them such that you get a dimensionless parameter. And so if you look up the units of viscosity, diffusivity, we know is meters squared per second. We know meters squared second, and then density, kilograms per cubic meter. And so if you apply all your units in here, in this particular group, you'll find it becomes dimensionless. So one number is the Schmidt number. There's also the Sherwood number. So if you recall, we had said if we have a mass transfer coefficient, we could estimate that as the diffusivity divided by the film thickness. So clearly this is dimensionless as well. So this is another dimensionless group. So these are the names of the researchers that did work on fluids, and so Schmidt number and the Sherwood number. Those are all about finding dimensionless groups among the governing parameters. So those parameters we saw in the balances, we can see them arising here. The Prandtl number, so the viscosity ratio to the thermal diffusivity, so the tendency, the conductivity. So this is like the momentum diffusivity divided by the thermal diffusivity. Remember, we said the diffusion for momentum is viscosity, and the diffusion for the energy balance is the conductivity. So we can see the Prandtl number, that's another dimensionless group. And here we have the Reynolds number, the diameter. So this is lowercase d, this is diameter, the velocity, the density, and the viscosity. And the Reynolds number is quite useful in determining the regime of the flow. So we had talked about problems where we had laminar flow. So that's where the flow is very irregular and we have parabolic velocity profiles and so on. And then if you keep increasing the velocity in that fluid, you come to a point where the fluid becomes turbulent. And knowing when that happens does matter to us, right? If we know that we are in turbulent flow, then that's going to change how much energy we need to put into the pump that's driving that fluid. If it's in laminar flow, there are certain limited mass transfer. So mass transfer may be more limited in laminar flow. So it's important to know where we transition from laminar flow to turbulent flow. So the Reynolds number helps us do that. So we have different applications for these dimensionless groups. So that's why they matter to us so much. So if you look at the meaning of these, so for instance, in the Prandtl number, if you found that you have a very large Prandtl number, then that will tell you that viscosity, that your momentum diffusion is much faster than your thermal diffusion. And that may mean that your fluid has a greater tendency to create friction than it does to dissipate heat. So that's a Prandtl number. The Sherwood number, you can see this relates more to the convection transfer rate as opposed to the diffusion transfer rate. So when we know we have a high Sherwood number, we know we get that the convection, that the bulk motion matters more than the diffusion, and possibly we can even eliminate some terms in our balances. For the Schmidt number, again, viscosity in competition with the molecular diffusion. So that tells us if this is large, or let's say this is low, then the molecular diffusion, the tendency for molecules to mix matters more than viscous drag, for instance. So we'll see in some of the exercises that follow that that developing these dimensionless groups gives us a useful way forward in classifying the nature of the problem we have. So for instance, if you calculate a Reynolds number and you find a very large number, you might be able to say, well, I can say this flow is turbulent, and in turbulent flow, radial gradients don't matter so much, right? So if you know your Reynolds number is very large, you can actually simplify your balance, in your conservation equation. It may be possible to eliminate certain terms in your balances and significantly simplify how easy your equations are to solve. And in fact, that was one of the main applications of these dimensionless groups. So when you were able to say, oh, if the Reynolds number is more than 2,100, we are turbulent and we can do this simplification, or if the Schmidt number is less than 2, then we are clearly, then the particle suspension doesn't matter as much. So there are lots of simplifications we can do once we have defined some criteria around these dimensionless groups. And the tremendous advantage that they give us is we can generalize these criteria. So because they are dimensionless, what we learn in one fluid can sometimes be transferred to another fluid. So for instance, in the flow of water, if we find that a value of 2,100 is where we transition to turbulent flow, then because this is dimensionless and we've basically divided out the fact that it's water, then if we have some other fluid, so if it's honey flow, for instance, and we can calculate the Reynolds number for honey, and it would have a different density and viscosity and so on. But the same criterion about the 2,100, that would also apply in the case of the honey. And then we would be able to use those criteria, that 2,100. We don't have to recalculate that every time. So not only are there analogies among momentum, heat, and mass transfer, in a sense, we can find analogies among the different types of fluid that we operate with. So that's what these dimensionless groups allow us to do. So it's a tremendous step forward when we have these. And I feel like a salesman going, but wait, there's more. Some of the other analysis that was done was when we analyze particular types of flow. So in this problem where this researcher, Blasius, was looking at solutions to flow over a flat surface, and finding and calculating these kinds of gradients. So like we've talked about before, you have concentration profiles, and we can talk about mass transfer coefficients and so on. So when you start looking at the solutions that you get there, you start to find relationships between these dimensionless groups as well. So it's not the case that we simply calculate these dimensionless groups, but we also find relationships between them. And for instance, in the Chiltern-Colburn analogy, you can relate the Sherwood number to the Reynolds number and the Schmidt number. And in the Reynolds analogy, you have this relationship, which relates all your dimensionless groups. And you can use these relationships then to find values for the coefficients that you possibly couldn't find any other way. So possibly you have limited availability of the constants that we need. So we know we need all these constants, the conductivity and the diffusivity. And so in principle, you need all these constants to solve fully the behavior of your fluid. But because we have the analogies, because we have these relationships among the dimensionless groups, we can take advantage of these relationships to find values of these parameters that we couldn't otherwise find. So for instance, we can actually use the Reynolds analogy to find a mass transfer coefficient. We can use the Nusselt analogy. We can find all these relationships and reduce the number of parameters that are needed. So that's generally speaking why these analogies matter to us so much. And in the next few lectures, we'll be looking at some nice examples in this area. So for right now, we just wanted to introduce the notion. So in this lecture, we've introduced the notion. We've talked about analogies among the different types of balances, and we've talked about the parameters and then the dimensionless groups and the fact that we can find criteria to tell us what kind of flow regime we are in. But more than that, we can also find relationships among these dimensionless groups, and we can really use that to progress our solution, our finding the exact behavior of the fluid. So you see, we started out with this very difficult problem that we have a complicated fluid, all kinds of possible variations are occurring in the fluid, and we had these multiple partial differential equations. But it is slowly starting to seem as if there may be enough relationships that we can realistically solve these problems and find solutions and be able to predict the fluid behavior. So now that that notion's introduced, we'll go into solving some of these problems and applying these analogies and understanding certain real-world cases.